All right, let's get started. Good morning. Okay, we got to try that again. Good morning. Okay, good. Exam 2 results came back. The average was 67, which is pretty good, actually. Not a bad average. It actually is a pretty good average for a difficult exam. So, good work there. The cutoffs for this exam are 90 for an A, 75 for B, 60 for C, and 40 is the minimum passing score on this exam. Once again, just like last time, these apply to just exam 2, nothing more and nothing less. Notice they're slightly different than exam 1. Each time we have an exam, we'll have a set of cutoffs for that exam only. At the end of the semester, we'll put everything together and come up with a set of cutoffs for the semester grade. Okay? But they're usually a little bit more generous than the cutoffs on the midterms. Usually, not always, but they should be pretty close. In other words, if you keep getting A's on every exam, you will probably get an A. But you will get an A. If you keep getting B's, you might get an A, but you probably will get a B. All right? Any question? Well, you don't have your exam back yet, but you should get your exam back sometime next week is my guess. All right? So if you're concerned about your grade and how you're doing, just let me know. Come to my office hour. We'll take a look at where you stand. Okay, today we're going to look at section 4.1. We're going to get into one of the most powerful applications of calculus in finding the maximum and minimum of a certain function. The problem we're going to concentrate on today is on finding the absolute maximum or the absolute minimum of some function f of x on the interval a to b. Okay, I'm going to sketch a few graphs here. We're going to find out what are the features that these two things must have and how to find them. So here's a graph of just kind of a random function. Let's say a is right here and b is right here. Okay, so we're going to only focus on the part of the function that's within a and b. Anything beyond a and b, we simply ignore them. So let's have something that looks like this. Okay, so it starts pretty high, it comes down, dips to kind of a low point right here, and then goes to kind of an intermediate value once we hit the right end of that interval. When you look across this graph here between a and b, the highest point is called the absolute maximum. And similarly, the lowest point right here, this is called the absolute minimum. I'll use MIN and MAX to abbreviate. So absolute max is the highest of all the possible y values, and absolute minimum is the lowest of all the possible y values. Okay, that's one possibility. Let me sketch a couple more. I want this one to look like this. Starts down here, goes up, and does that. Okay, starts low and goes up, kind of go through a couple of peaks and valleys, and then go to the point on the right. And so once again, the lowest point right here, this is our absolute minimum. No other point on that graph is lower than that point. And similarly, this one right here is the absolute maximum. I can find no other higher y values on that graph within this interval. Outside A and B, something else might be happening, but we don't really care about that when we look for the absolute max and min. This one right here, this is called a relative maximum. It's called a relative because it is clearly not the highest point, but it is the highest point near that point. Okay, so relative max is the highest in the neighborhood. But notice that there's another point higher than that. So this could be the highest building in a little town, but clearly it's not the highest building in that country, right? Math building is the highest building on the Purdue campus, but it is clearly not the highest building in the city and clearly not in the state. So it's relative to something nearby, but not the highest. This one right here is the relative minimum. We'll talk more about relative max and min in a later section, but for now we're going to focus on just the absolute stuff. Okay, let me sketch two more, and then we can find out what kind of features we have to look for when we try to find these things. For this one, I want it to look like this. Okay, so a check mark, V-shaped kind of thing. Again, focusing on just the absolute max and min for now. And I'll sketch one more, and then we'll point out the important features. This one, I want it to look like this. And there we have an absolute maximum, an absolute minimum here, and this guy has an absolute maximum. Okay, now look at the four graphs that we just sketched. Where do you think are the possible locations of absolute maximum or absolute minimum based on the four graphs we just saw? Where might they occur? What do you think? Yeah. Right, yeah. That's one good place to look for it. If you look at the first graph right here, notice that this is a region where the tangent line is horizontal. That means f prime is equal to 0, right? But that's not guaranteed to be an absolute max or min. It helps you find a relative max or min. Where else might they be? Right. Yeah, where does it occur? So we're looking for where they might occur. And he pointed out that we could look for where the tangent line is horizontal. What are the other locations where we could look for them? How about the boundaries? Right, look at the first graph. At the end point on the left, we have an absolute maximum. On the second graph, we have the absolute max and min at the two ends. So one place to look for them is right here, where f prime is 0. Another place to possibly they might occur are the endpoints of the interval. How about these two, the graphs 3 and 4? What's the derivative right here? Does not exist, right? Right, because it is not smooth, right? How about this guy right here? Exactly. Okay? But notice that even though the derivative does not exist, they could still be potential locations of absolute max or min. So now we know what to look for. We look for where the tangent line is horizontal, where the tangent line slope is undefined, and also the end points. So we know that the possible locations of absolute max or min are where f prime is equal to 0, where f prime does not exist. Right? So equal to 0 covers the first graph, possible locations. Does not exist when we have these sharp corners, and also the endpoints of the interval. So at x is equal to a, and at x is equal to b. All right, does that make sense? Yeah? Okay, so when I give you a function and an interval, that's what we're going to be starting with. Find out where they are. And once we found them, we simply find out which one has the highest y value, and then which one has the lowest y value. Then we see which location, possibly plural, give us the highest / lowest y values. Okay, let's try this on something. Function is 2x cubed minus 6x squared minus 18x plus 4. And we're going to consider the interval from -2 to 4. If you're able to sketch this, which, by the way, if you can't, not a big deal. But if you're able to, we'll see something that looks kind of like this. Okay, something like that. And again, if you can't sketch that, it's not a big deal. We know a systematic way to find where the maximum and minimum are. Okay, so here's my function, my interval. First, we're going to look for where the derivative is 0, where the derivative might be undefined. These places, by the way, are called critical numbers. You can find x where the derivative is 0 or undefined in the interval that we care about. Those are called critical numbers. Based on the graph here, we expect to see 2 of them. So let's see. Let's take the derivative. We get 6x squared minus 12x minus 18. All right, let's find out where this is equal to 0. Notice I can reduce by 6. And then I can factor that. I want a minus 2, so I want a minus 3 here and a positive 1. Right? So this tells me that x is equal to minus 1 and x is equal to 3. All right, so these are the critical numbers because these numbers make the first derivative equal to 0. They tell us where the tangent line is flat. And those are potential locations of maximum and minimum. Because we know what the graph looks like, which generally we may not know that, we can already see that's going to be the location of that. But let's go through the method. Now we check where f prime is undefined. And where does that happen? Where might this function be undefined? Say it again? Right. Good. What kind of function is this? Quadratic is a class of what? Polynomials. Good. Yeah, this will never happen. Okay, never, because remember, polynomials are always defined. Okay, so that's all we can find out of these 2 criteria. F prime equal to 0, F prime undefined. We got these 2 possible locations. Okay, now we consider these 2 together with the endpoints, and we find out which one gives me the highest value of y. Now we compare f of x at the critical numbers and the endpoints. All right, so starting with the lowest value, it's the left end point. I want to see the value of the function at the left end point. minus 2. And then I have two critical numbers before I get to the right. So there are minus 1 and 3. And finally, the right endpoint at 4. Pay special attention that we're not using f prime or using f, the function itself, because f tells me how high or how low the graph can get. That's what I want to find. At the left endpoint, we plug f minus 2 into the original function. And if I do that, it turns out I get 0. Then I repeat that with minus 1, plugging into the original function. So I end up getting 14. I did this beforehand. Repeating that with 3 into f again, we get minus 50. And finally at 4, we get negative 36. And these tell you how high or how low the function can get. The largest of all of these is the absolute maximum. So 14 is bigger than all of these things. So that's where our absolute maximum is. Our absolute maximum occurs at x is equal to minus 1, y is equal to 14. Then we look for the minimum, the lowest of all of these, and that's minus 50. And that's going to be our absolute minimum. Okay, so that's how we do it. You find out the locations of the zero tangent line, undefined tangent line, then compare them to what happens at the end. Whichever comes out on top is our max. Whichever is at the lowest value is our minimum. Does that make sense? Any question on that example? Okay, let's do more example. And this next example, I want to point out something very important that you have to look out for. Let's look at x plus 1 over x on the interval from 1 to 4. Same set of procedures. We look for where the tangent line is horizontal. We look for where the tangent line is not defined. That's where a cusp or a corner could be. And then we compare to what happens at the end and look for the max and min. F prime is 1 minus x to the minus 2, right? So 1 minus 1 over x squared. First, let's find out where this thing might be 0. If you multiply both sides by x squared, we get x squared minus 1 equal to 0. That means x is equal to minus 1 and x is equal to 1. Okay, so these are where the tangent lines are horizontal. We have two possible locations. Now take a look at this location here. You see anything wrong with this location? Right, it's outside the interval that we care about, right? Here it was saying that find me the highest and lowest within this interval only. Anything outside we completely ignore. This happens to be outside, so we actually don't want to consider that. It falls outside that interval. The last example, the two numbers we got happen to fall inside. But here, this is something that can happen quite often. You may come up with the numbers that are outside the interval. You throw them away. Okay, now we look at what happens when f prime is undefined. Well, that's pretty clear at 0, right? And this one we also throw out for two reasons. One, it's outside the interval. Also, f is not defined there. Therefore, it cannot be the location of an absolute maximum or minimum. Right? It cannot be the highest or the lowest value of the function if it's not even defined there in the first place. It has to exist. That point simply does not exist. So we threw that out for two reasons. Outside the interval and also not in the domain of the function. Okay, the only value that we kept happens to be the same as the left endpoint. That's okay. That's okay. So now we compare what this function gives me at the left endpoint at whatever critical number I kept. It's also 1, not a big deal. And then at 4. And once again, you go back to the function itself. You're interested in the height of the point, not the slope anymore. So f of 1 would be 1 plus 1 over 1, and that's a 2. F of 4 would be 4 plus 1 over 4, and that's 5 over 4. No. 17 over 4. Okay, whichever one's the highest one is the absolute maximum. Whichever one's the lowest one is the absolute minimum. Let's see. This is 4. That's more than 4. So, of course, it's more than 4. So that's our absolute max. No other point on this function within that interval is higher than this value. And this is our absolute minimum. No other point on this function within that interval is lower than this. Everything is strictly between 2 and 17 over 4. Okay, any question on this? Okay, does the general process make sense? Yeah? All right, let's do another one. Let's look for the absolute maximum and the absolute minimum of the function x times e to the minus x squared over 32 on the interval -2 to 8. Same procedures, right? We find where the tangent line is horizontal. We find where the tangent line is undefined. And then we compare to what happens at the endpoints. Find the highest and lowest, and that's it. All right, so let's do the derivative. How do we find the derivative here? What rule? Product rule, good. So let's do the product rule. You got to use the product rule because that's the product of two functions of x, right? There's a function of x times a function of x. So that's a product rule situation. And we get first times the derivative of the second. Second is the exponential part. We get e to the negative x squared over 32, right? What else? Chain rule, that's right, chain rule. Times the derivative of the power, and that's going to be negative x over 16. First derivative of the second. Remember to use the chain rule. Plus the second part times derivative of the first, and that's a 1. Okay, let's clean this up a little bit. Okay, so just like last time, now we're interested in where this thing might be 0 and where this thing might ever become undefined. Let's factor out this e to the something. So here we wrote this entire thing as e to the something times, here's a quadratic function, minus 1 over 16 x squared plus 1. Now we find out where this might be 0. Yeah. Very good. That's one of the reasons why we wanted to factor this out. So what he said here is we already know we don't have to worry about this part because e to the anything will never be 0. You can make it close to 0, but you can't make it exactly equal to 0. So let me write that down. Rather, or. So technically, we got to consider both of those. But this can never happen because we know that the exponential function exponential functions don't have x-intercepts. And when we ask for where this thing is equal to 0, we're asking for locations of x where the value of y is equal to 0, and those are our x-intercepts. So that one we ignore. That's not going to contribute anything meaningful. The second part is pretty easy. Right? This is x squared minus 16 is equal to 0. So we get x is equal to minus 4, and x is equal to 4. Okay, what do we have to check with those two things? Right, if they're within the interval. Are they? We only care about between -2 and 8. Right, that one is outside, so we throw that out. That one is okay. That's a square. 4 is okay, we keep that. All right, so how about f prime undefined? Where might this happen? Can it happen? Can this thing ever become undefined? Why not? What kind of function is this? What family of function is that? Polynomial, what family is that? Exponential. Both of these are defined for all values of x. So the product of those two things will also be defined for all values of x. I'll write that down. Never. Because exponential and polynomial functions are defined for all x, right? All real numbers of x. If they're both defined for any value of x, their product is also going to be defined for all values of x. That thing is never undefined. That thing is never undefined. The product of those two will never be undefined. Okay, so that gives us 3 values of x to consider. You always have 2 for your endpoints, and you have however many critical numbers you end up getting and keeping. We have those 2, we have that one. Now we compare. First, let's check out what happens at the left endpoint. Then whatever critical number I kept, which is 4. And then the right endpoint. Left, right, and whatever number we kept in the middle. Okay, now we take those values back into the function at the top. So this is -2 times e to the negative 2 squared over 32. So that's -2 times e to the -4 over 32. This turns out to be around minus 1.76. Repeat. This turns out to be around 2.43, and this turns out to be around 1.08. The largest of these 3 is the absolute max, right here. The smallest of these 3 is the absolute minimum. It's possible for 2 of these to have, or even more of these to have the same value. And that happens when you have multiple locations of absolute min or multiple locations of absolute max. Questions? All right, let's do one more. Let's find the absolute max and min of the function x minus natural log of 9x. The interval we care about is from positive 1 over 2 to 2. Same procedures. Take the derivative. Derivative of x is 1. What's the derivative of natural log of 9x? Right, 1 over 9x, and then multiplied by 9 by the chain rule, right? Derivative of natural log of anything is 1 over that something, and then derivative of that something, right? Chain rule. And this is equal to 1 minus 1 over x. Let's find out where this might be 0. Multiply by x. And we see that x is equal to 1. Do we keep it? Right, we keep it because it's within the interval 1/2 to 2, right? If it falls outside, we throw it away, but it's within there, we keep it. F prime does not exist, very clearly happens at 0. But we throw this out for 2 reasons again. 1, it's outside the interval. 2, the function is not even defined at 0. So it cannot possibly be where the absolute max or minimum can occur. So whichever reason you use to throw it out, you got to throw it out. It's not something we want to keep. Okay, so now we have 3 values of x to check. Look at the value of the function at the left endpoint, the right endpoint, and then the critical number that we kept. Okay, now we got these 3 things here. You can check this with your calculator, but this happens to be the largest value of the 3, this guy right here. And then again, check with your calculator. This happens to be the absolute minimum because it's the smallest of the 3. This one right here is somewhere in between the 2, so it's not an absolute maximum or minimum. It can still be meaningful depending on what you're looking at this for, but for the purpose of finding the largest possible and the smallest possible, that one doesn't do anything. All right, that's it for today. See you Wednesday.